Okay, let's get started with some questions on stack today. There are about 15 to 16 questions on stack which we would try to solve today. The first question: given a string containing n s's and n x's, where s indicates a push operation and x indicates a pop operation, and with the stack initially empty. The question is to formulate a rule to check whether a given string S of operations is admissible or not. What we have is a string containing only two letters. The one letter can be S, the other can be X. S is a push and X is a pop. And the string clearly can have has equal number of s's and equal number of x's. So one example could be if n is equal to 3, then sss xxx is a string, and sss xxx is a valid string because if you do 3 pops and 3 pushes and then 3 pops, so that's a valid string. But if you have S and XX and then SS and then X, that is not a valid string because you do a push and then you try to do 2 pops. The second pop is obviously going to fail, so that's not a valid string. So let's try to solve this question. So here is the answer to question number 1. The algorithm says that scan the string and keep a count of number of elements in the stack. The number of elements in the stack has to increase when the push operation is done, and the number of elements on the stack has to decrease when the pop operation is done. So when we start scanning the string, if a S is encountered, then increment num elements in stack, and if a P is encountered, then decrement num elements in stack. At any point of time, if we find that num elements in stack becomes negative, then it means the string is not valid. So let's go back to the examples which we took. If we had SSS and XXX, so first S, second S, third S, that makes 3, and then XXX causes 3 minus 1, which is 2, 2 minus 1 equals to 1, and 1 minus 1 equals to 0. So as we scanned through the string, there was no point where we encountered a negative number. So that means SSS and XXX is a valid string. But if you look at the case where we have SXX, so S is plus 1, so we have the positive number 1, and then we encounter the second X, so it becomes 0, and then the second X, so it becomes a minus 1. So SXX something is not a valid string. So that's about question number 1 and the corresponding answer. Now let's get into the second question. The second question goes like this: given a stack, how to reverse the content of stack by using only the stack operations push and pop. So my function has to take a reference to a stack object, and the function reverses the content of the stack. The question is to implement a function which does that. So let's try to find out how to solve this question. Now there are multiple answers to this question, and the first one is a non-recursive solution. The answer goes like this: assume that we have a class called myStack which implements a stack of integers. So as we already said, we have to write a function which takes reference to myStack class and reverses the integers in the past stack. So here is the first solution, which is a non-recursive one, and what we do is the function reverse stack takes a reference to an object of type myStack, and the function returns void. Inside the function we have two temporary myStack objects, which is ts1 and ts2, and a temporary integer called elim. So what we do is we start popping out elements from our stack S and start pushing it to ts1. So the first while loop pops elements from stack S and pushes it to the temporary stack ts1. So when this while loop completes, what would happen is if all the elements of the stack S would become empty, and the stack ts1 would have exactly the same contents as S. The only thing is the ts1 is going to have the elements in the reverse order. But this doesn't solve the problem, because we wanted the stack S to be having elements in the reverse order. So to achieve that, we have a second while loop which starts popping elements from the stack ts1 and pushes it to stack ts2. So the while loop again runs until the stack ts1 gets emptied. So the stack ts2 would again contain elements same as stack S and in the same order. So at the end of the second while loop, we have nothing in stack S, nothing in stack ts1, and the stack ts2 has all the elements as stack S. So then we enter into the third while loop, which just pops elements from ts2 and pushes it to stack S, which is a reference to the stack which is passed to this function. And once this while loop is complete, the stack S will have all the elements in the reverse order. So this is the non-recursive implementation of the problem. Now let's look at a recursive solution to this question. So the function is again called reverse stack. It takes a reference to myStack object and returns void. What we do in this function is we have a temporary integer element. We pop the topmost element of the stack. After popping the element, we call the reverse stack function again with the same stack S, and then after return from the stack S, we call the method move to end. In the stack S, the element which was just popped. So what we are basically trying to do is, in a recursive fashion, we pop the topmost element of the stack and then reverse the remaining stack, and once the remaining stack has been reversed, we move the element which we just popped to the end of the stack, which is already reversed. So it is important that now we look into the method move to end. Move to end function returns void, takes a reference to myStack and integer elim. In this function, we pop the top element from the stack and call the function move to end, pass it the stack S and the elim, and then we call s.push tlim, and on the else part we call s.push elim. So let's try to understand what is happening. Alright, so what we do is we first pop the topmost element from the stack, and then we move the element in the remaining stack S. We try to move it towards the end, and then once this is moved to the end, we call s.push the element which we just popped. And if the stack S was did not have any element, we know that uh, this is already the end of the stack. So what we do is we call s.push ln. So this is the non-recursive implement. This is the recursive implementation of the question reversing the stack. Question number 3 is towers of Hanoi. You basically have 3 rods and n disks of different sizes which can slide onto any tower. The puzzle starts with disks sorted in ascending order of size from top to bottom, which obviously means that each disk sits on top of an even larger one. We have the following constraint. First of all, only one disk can be moved at a time. Second constraint is a disk is slid off the top of one rod into the next rod. A disk can only be placed on top of a larger disk. So with these 3 constraints, what we have to do is write a program to move the disks from first rod to the last using stacks. Okay, so before we delve into the code and the algorithm, let's take one example of moving plates from rod A to rod B, rod A to rod C, and the rod A has just 2 plates and they are called plate number 1 and plate number 2. So the steps are going to be as follows. The first thing which we do is to move one from A to B. The next step is to move 2 from A to C, and then the third step is to move 1 from B to C. So C now has 1 to 2, and none of the constraints which we had was violated. So let's take the case where rod A had 3 plates, 1, 2 and 3. So in this case what we do is move 1 from A to B, move 2 from A to C, move 1 from B to C. So at this point what we have is that plate number 1 to 2 is on C. Then we move 3 from A to C, okay, this has to be this actually has to be move 3 from A to B. And then move 1 from C to B, move 2 from C to A, and then move 1 from B to A. So now again on rod A we have 1, 2, and rod B contains 3. Then we move 3 from B to C, and then the whole idea again is to just move 1 and 2 from rod A to rod C. Okay, so the important point over here is that the algorithm for moving plates 1, 2, 3 from A to C can be rewritten as move 1 and 2 from A to C, move 3 from A to B, move 1 and 2 back from C to A, move 3 from B to C, and move 1 and 2 from A to C. And that's the basis for the recursive algorithm which is shown on this slide. So the function is called as move. It returns void. It takes n, which is the number of plates which are there on rod A. It takes a reference to stack S, which is a source stack. The source stack is the rod A, which has all the plates initially. The second stack is the third parameter to this function is a reference to stack T, which is the target stack. So T stands for the target stack, and we also have a temporary stack which is passed in over here. So the first thing which we have in this function is a check if n equals to 2, which is the simplest case of moving 2 plates from rod number A to rod number C. which is simple and which we all know. What we do is we pop the plate number 1 from the source stack and push it to the temporary rod. Then we pop the source stack and push it to the target rod, which is the plate number 2. And the third thing is to do is to pop the plate number 1 from the temporary rod or temporary stack to the rod number C. So this is the case where we have this is for the case where we have just 2 plates. And then we have a recursive call to the move function, which says move n-1 plates from source to target stack and use temp as a temporary stack. And once we have done that, we have only the nth plate on the source stack. We pop that nth plate and push it to the temporary stack. Once we have done that, we move n-1 plate. So we call the function move recursively again. So we call move n-1, and this move has to move n-1 plates from the rod C, which is the target stack, back to the source stack or rod number A. So we call move n-1, and the parameter source and target are modified here. So the source is actually T here, and the third stack here is a T, and there is also a temp stack. So once the n-1 plates has been moved back to rod number 1, what we got to do is pop the plate which is the nth plate from the temporary rod or the temporary stack and push it to the target stack. And then once that has been done, our job again is to move n-1 plates from the source rod or the source stack to the target stack. So as you can see, there are 3 recursive calls to move over here. So this is the recursive implementation for the towers of Hanoi problem. Let's move to question number 4. The question here is, write a program to sort a stack in ascending order. You should not make any assumptions about how the stack is implemented. The following are the only functions that should be used to write this program: the push, the pop, and the peek, and the empty. So these are the operations which are allowed on a stack, and these are the only functions which should be used to sort the stack in the ascending order. So again, for this question we have 2 implementations. The first one is little similar to what we saw for reversing of elements, and this is a recursive implementation. Let's go over the solution. So we have a function called sort stack, which returns void and takes a reference to my stack object. There is a if check if s.peak is not equal to, which means that basically if there is no element in the stack, so you got to return from this point. If the stack is not empty, we pop an element from the stack and store it in a temporary variable called t, and we call the method sort stack with the parameter s. So all we are trying to do is we just pop an element from the current stack and then call the method sort stack recursively with an element lesser than the actual content of the stack. And once we return from sort stack, we know that my stack is sorted other than the element which we popped in this function. So all we got to do is add this element at the right place in the sorted stack. So we call the method add element to sorted stack, in which we pass the stack s, which has n-1 elements, and the element t which was popped in this function. Let's go and try to understand the implementation of add element to sorted stack now. The function add element to sorted stack now takes a void, returns void, takes a reference to stack object and the integer elim. So the stack S is sorted, and what we got to do is we got to put this element which is the second parameter to this sorted stack, and what we do in this method is we pop the first element of the stack T1. If T1 is greater than elim, or rather if element is lesser than T1, so which means that we are at the right place to insert this element. So we push T1 and then we push the element and we return from this function. But if T1 is not greater than element, then we call the method add elim to sorted stack. We pass the reference to S and elim, and then we call s.push. So this is how the stack is going to be sorted using this recursive function. Now let's look at approach number 2, which is a non-recursive function. So in this case what we do is we have a function sort stack which returns void and takes a reference to my stack object. We create a temporary stack called T inside this stack, and while S is not equal to empty, what we do is we pop an element from S, and if we just check if the element which is popped is less than the element which is there in stack T. If that is the case, then we push the element, we pop the element from the stack T and push it to stack S, and then once that has been done, we call T.push with E1. So what will happen is when this while loop ends, we will have the stacks sorted in T. Excuse me. So the last while loop is to move all the elements from T to the source stack S. Okay, let's get started with question number 5. The question is to find the minimum of a stack. How would you design a stack which, in addition to push and pop, also has a function min which returns the minimum of element? And the constraint or the requirement here is that push, pop and min should all operate in O1 time. There are multiple ways to solve this problem, and before looking into the source code, let's see what is the solution number 1. So in the solution number 1, what we do is every node maintains the minimum of the stack. So what we are suggesting is that every node of the stack, in addition to having the data element which is of type integer, we would also have the minimum of the stack, and the minimum maintains the minimum of the stack till that point of time. So if we have 3 elements in the stack, the topmost element would have the minimum of the stack which has 3 elements. So when you do a push operation, the current minimum of the stack is compared with the value which is being pushed, and the smaller of the two is stored in the minimum of the stack. So this is how we are going to do the push operation. Now let's jump into the source code. So on the right side we can see that we have a class called node with minimum, and this, in addition to having a value variable which is of type integer, we also have a minimum variable which is of the same type. There is a constructor defined for this class node with minimum which takes the value and the min and assigns it to the data member's value and min. The second class is class stack with min. This is derived from the public stack class, which is a template class with the template type set to node with min. Now let's see what we do in the push operation. The push returns a void, takes an integer value, and the first thing it does is it compares the value which is to be pushed with the current minimum of the stack. And how do we find the current minimum of the stack? By just calling the method min of this class. And the new min, once we have the new min, we create a new node with the value and the min and push that to the stack. That's what we just have to do in the push operation. There is another method which is min. What it does is it initially checks if the stack is empty. If the stack is empty, it returns a max value of integer just for the user to know that there is nothing in the stack. Else, if there is something in the stack, it does a peek and returns the min field of the node which is returned as a part of the peek. That's the first solution. The problem with the first solution is that the original stack had to be modified for this functionality to be implemented. There may be times when people may not want to actually modify the original stack. So what we got to do is, in this second approach, instead of maintaining the variables in the same stack, instead of maintaining the minimum value in the same stack, we just move out that min variable to a different stack. What happens is the algorithm remains the same as the previous one. The only difference is that instead of creating a node with the value and the min, we calculate the min as usual and push the min value to a different stack. Now this is second solution, in which the stack depth or the size of the stack remains the same as the size of the other stack. But what we can also do is we can do some optimization in this case, which is we don't have to continuously maintain the min if it continues to be the same. So if the top element of the minimum stack is continues to be less than the current element to be pushed, we know that the minimum of the stack remains the same. So there is no need to again create a node for the same minimum in the stack. So this is little optimization which can be done. So now here is the code. So let's directly go into the push operation. Push takes a integer value, compares the current min of the stack, and if the value which is to be pushed is less than or equal to min, we push that into the supplementary stack, the additional stack s2.push, and the element anyway has to be pushed to the super stack super.push. What pop does is it pops the element from my stack, it compares that to the min of the stack, and if that matches, we know that the minimum also has to be removed. So the s2 stack is also popped out, and the min, as usual, all it got to do is peek on the stack s2 and return the value, and if the stack is empty, just return an integer max value. There is a third solution here, which is again by modifying the stack elements, and the suggestion here is that every node has two pointers. The first pointer is for the stack and the second pointer is to link the nodes in a linked list of ascending order. So the top points to the usual top of the stack, and there is another pointer called min list which always points to the minimum element of the stack. So this is the list, this is the linked list, and the min list would always point to the minimum element because we want to keep the stack in the ascending order. So note that the push and the pop operation does not operate in O1 in this case, because in addition to pushing the element to the stack, we also have to go and update the linked list. And here is the code. We can just go through it and understand. It's pretty trivial. Okay, question number 6. So this question is about implementing two stacks using one array. Write a routine to implement two stacks using only one array, and your stack routine should not declare an overflow unless every slot in the array is used. Okay, so what we do is the stack 1, the first stack, should grow from index 0. It should start from index 0 and grow towards index n of the array. And the stack 2 should start from index max array size and it should grow towards the index 0. Unless there is no element in array, both the stacks grow. And we have the source code in the next slide, so which is pretty easy to understand. I have a myStack class, and when I call the push operation, I take in addition to the number which is to be pushed, I also take a parameter which indicates which stack I need to push the data into. And in the push, we just do a diff of top 2 minus top 1 and see if that is equal to 0. That means there is a stack full condition. Otherwise, what we do is we just see which is the stack in which the data has to be pushed and put the element in that particular stack. Similarly, let's see the pop operation. So pop again checks the stack, which stack this belongs to, and depending on which stack this belongs to, it would just pop the element from the corresponding stack. So in this case, it is nums top 1 minus 1 if it is stack 1, and this is index top 2 plus plus from the nums array. Next question is, how would you use single array to implement 3 stacks? So the previous question was about implementing 2 stacks in one array. Now we talk about implementing 3 stacks in one array. Okay, so the first stack should grow from index 0 towards index n. The second stack should start from index n and go towards index 0. And now what about the third stack? The third stack actually has to start somewhere in the middle. So what we can do is we can allocate equal amount of spaces, assuming that all these stacks would be of almost the same size. So if the array has 60 capacity, then we would probably start from index 0 for the third stack, so that the first stack we provide a space from index 0 to 19, the second one from 19 to 40, and the third one from 40 to 60. We need to keep the following information: the index of the first stack, that is the top of the first stack, which is top 1, the index of the second stack, which is top 2, the top 2 of the second stack, the starting index of the third stack, and the top index of the third stack. So for the first and the second stack, we just need to maintain the top information, and for the third stack we need to maintain 2 pieces of information. First thing is the starting index, and the second is the top element of this third stack. Push operation. For pushing onto the first stack, we need to see if adding an element causes it to bump into the third stack. So this is the only problem which we have. Otherwise, it's a very straightforward push. If it is going to bump into the third stack, we have to shift the third stack on the right side just to create space for the first stack. If we are pushing the element into the second stack, we need to see if adding an element causes it to bump into the third stack. If so, try to shift the third stack leftwards. So all we are trying to achieve here is just to make sure that when there is space available, then we don't declare a stack full for any of these 3 stacks. There is a severe overhead here. If you start bumping into the third stack, you have to move the elements leftward or rightward, and which is a very inefficient solution. Maybe there is an optimization possible, in the sense that when you decide that the elements of the stack 3 has to be shifted, so instead of just shifting it by one, you can do a dual shift and create much more spaces. Question number 8 is implement a myQueue class which implements a queue using two stacks. I have two stacks with the operation push pop peek is empty, and I have to implement a myQueue class which implements a queue using these two stack operations. Okay, so let's just read out this text. Since the major difference between a queue and a stack is the order, first in first out versus last in first out, we know that we need to modify peek and pop to go in reverse order. We can use our second stack to reverse the order of the elements by popping and pushing the elements onto S2. In such an implementation on in pop operation, pop everything from into S2, perform the peek pop operation, and then push everything back. Because what we intend to get is the first in first property. This will two pop are performed back to back. We are neatly moving elements. We can implement a lazy approach where we let the elements sit in S2. S1 will thus be ordered with the S1 will thus be ordered with the latest elements at top, while S2 will have the elements on top. Just a new element onto peek and pop S1. When S2 is empty, we will transfer all the elements from S1 into S2 in reverse order. Easy to understand. Let's see the code. So I have a myQueue class over here, and there are two stacks inside it, S1 and S2. Okay, there is a constructor which just creates these two stacks. When I ask for the size of the stack, it gives me the S1 dot size plus S2 dot size. There is a method called add which takes a value, and what it does is it pushes the element into the S1. So we always do a push into S1. Now let's look into the method remove. So what could happen is that S2 is not empty, and if S2 is not empty, we have to return the topmost element of the S2, because the topmost element of S2 was the one which was the first element which was added to the stack, to the queue. If S2 is not empty, what we do is, until S1 is empty, we pop elements from S1 and push it to S2, and then we return the topmost element of the S2. So the addition is always done to S1, and the removal can put the element, either it returns from the S1 stack, or it pops the element and gives it back. Question number 9. So imagine that we have a stack of plates. So if the stack gets too high, it might topple. Therefore, in real life, we would likely start a new stack when the previous stack exceeds some threshold. So the question here is to implement a data structure or a class called set of stacks that mimics this behavior. Set of stacks would be composed of several stacks and should create a new stack once the previous one exceeds capacity. Set of stacks push and set of stacks pop would behave identical to a single stack. That is, pop should return the same value as it would if it were just a single stack. There is a follow-up question which we would not try to solve today. The follow-up question is to implement a function pop at which takes a integer index and which performs a pop operation on a specific substack. Okay, so there are going to be a couple of classes which we need to add. The first one is of course a set of stacks, which is the class which we need to implement as a part of the problem. But before we start implementing the set of stacks, we also need to implement a class called stack of stack pointers. So this is a class stack of stack pointers which has an array of pointer to stack objects, and there is a max, which is this is the maximum number of stack size which we can have. And the push takes a pointer to the stack and adds it to the my stack, and the pop just returns takes out the topmost element of the pointer stack pointer and returns it, and the peek just returns the topmost element. So this is the stack of stack pointers. Now we get into the class set of stacks. So the set of stacks is going to contain an object stack pointers of type stack of stack pointers, and this obviously has a method called push and pop. Push takes an integer, pop doesn't take anything. Okay, so let's see what we do in the push operation of the set of stacks. This method takes an integer and returns void. So the first thing which we do is we call peek method of stack pointers, and this is going to give me the pointer to the topmost stack in the stack of stack pointers. If this stack is full, this is an indication that we need to create a new stack. So what we do is we new up a stack object, call the push of this stack, and then push the stack pointer itself to the stack pointers object, and then we return from here. But if the stack which we got from the stack of stack pointers is not full, what we do is we just call the push. By the way, this should be t push. So what we do is that push the element in the stack. Similarly, pop should get the top of the stack, and if the stack gets empty, then pop it from the stack of the stacks. Question number 10. Describe how stacks can be used to check balancing of symbol. So we get an expression or a sequence of text, and this is going to have multiple symbols like left parenthesis open, right parenthesis close, and it could be a comment, starting comment like C style comment. It could be square brackets, and the problem statement says that all of these can be mixed up. I don't have an example over here, but any expression, for example, can have a left parenthesis and right parenthesis. So if an expression like that is passed as an input to this function which we are going to write, then it should say whether it has symbols which are balanced or not. So this is the answer to that. The first thing which we do is create a stack, and while end of input is not raised, if the character read is not a symbol to be balanced, ignore it. So now when we say that the balance symbol would be some of these three things: the left bracket, the left square bracket, the left curly bracket, or it could be a closing bracket. If the character is an opening symbol like left bracket, left square bracket, or left curly bracket, push it onto the stack. If it is a closing symbol, then the report error, if stack is empty, so if the stack is empty, report error, otherwise pop the stack. If the symbol pop does not correspond to the character just read, then we have an error case. So this is simple. Whenever the opening bracket is encountered, that character has to be pushed into the stack, and the moment you see a closing symbol, you just got to pop an element from the stack and see if that matches with the character which we just read. If the end of the input is reached and stack is not empty, then it means that there is some error and the symbols are not balanced. Question number 11. Infix to postfix. So discuss infix to postfix conversion algorithm. All of us know what is infix and what is postfix. If the expression is 2 plus 3, 2 plus 3 is the infix notation, and the corresponding postfix is going to be 2 3 plus. If the expression is 2 plus 3 star 4, then we would have 2 3 4 star plus. 2 3 4 star plus is the postfix form of the infix 2 plus 3 star 4. So these are a couple of examples of infix and postfix expression. So let's see how do we solve this. So what we do is we create a stack. For each character t in the input stream, if t is an operand, so there are two kinds of things. One is an operator and the other is operand. So all the variables in the expression, they are called as an operand. They are the operand. So if t is an operand, we output t because we don't need to stack the operand. Else if t is a right parenthesis, pop and output tokens until a left parenthesis is popped. Else pop an output token until one of the lower priority than t is encountered or a left parenthesis is encountered or stack is empty. So what is the nature of the stack here? In case the operator which I just read has a precedence higher than the topmost element of the stack, we just got to push the operator to the stack. For example, if we are working on 2 plus 3 star 4, then plus would be there in the stack when we are reading star. So this star can be pushed into the stack because it has a higher precedence compared to the topmost element of the stack. The problem comes when you have a star in the stack and the character read is plus. The stack cannot remain in this order, so we got to pop the stack until we either empty the stack or we reach a state where we have an operator which is having a lesser precedence compared to the operator just read. So just follow this algorithm and you would see that the infix expression gets converted to the postfix expression. Question number 12 is to evaluate a postfix expression. So write a program to evaluate postfix expression. Okay, so we scan the postfix string from left to right, initialize an empty stack, and repeat the below steps. Here it is mentioned as step number 4 and 5, but it's basically the below 2 steps. So if the scan character is an operand, push it onto the stack. So in this case what we do is we push the not the operator but the operands onto the stack. So let's take an example. If it was 2 3 4 star plus, when we read 2 we would push it into the stack, when we read 3 we would push that into the stack, when we read 4 we would push that into the stack. If the scan character is an operator and if the operator is unary operator, then pop an element from the stack. If the operator is a binary operator, then pop 2 elements from the stack, apply the operator to the popped element and push the result to the stack. The punchline is whenever we read an operator into the input stream, we just have to pop either 1 or 2 element depending on whether it is a unary operator or a binary operator, evaluate that expression and put the result back into the stack. In case of 2, 3, 4, star plus, when we read star, we know that star is a binary operator, so pop 3 and 4 from the stack, multiply them, which is 12, and push the result 12 back to the stack. So the stack is going to have 2 and 12. After all characters are scanned, we will have only one element in the stack, and that is the answer. Question number 13 is how to implement a stack using two queues. And this is similar to the question which we discussed little earlier of implementing a queue using two stacks. So let's directly jump to the source code, or let's just have a few notes over here. So the queue has an operation add, remove, and empty, which indicates that the queue is empty. So when we create the stack object in the constructor, we would create two queues, q1 and q2, and we would say that the active queue is q1 and the inactive queue is q2. When we push an element to the stack as seen in the source code, we would always push the element to the active queue. Since active queue is set to S1 at the start, so what happens is we initially push the element into the stack S1. And if a pop is done, if the active queue is not empty, then we call active queue dot remove. This should actually be active queue dot pop, because what we this has to be removed. Basically, we remove an element from the active queue, and we would just add it to the inactive queue. So keep taking out element from the active queue and then keep putting it to the inactive queue. And if we have reached an empty condition, we just got to swap the variable active queue and inactive queue and return n, because we know that that's the element which is the last element which was added. So this is how we would implement a stack using two queues. Question number 14. Question number 14 is consider an empty stack of integers. Let numbers 1, 2, 3, 4, 5, 6 be pushed onto this stack only in the order they appear from left to right. Let S indicates a push and X indicates a pop operation. Can they be permuted in the order 3, 2, 5, 6, 4, 1 and order 1, 5, 4, 6, 2, 3? If a permutation is possible, give the order string of operations. So let's just take an example. If I do a S and X, then when I do a S I would push 1, and if I do a X I would get 1. So the output is going to be 1. If I do SSS XX, the output is going to be 3 and 2. So what we really got to do is just look into this output string and based on that try to find the corresponding string of S and X. So the first one is 3. So to get 3 we need to push 3 elements. So it has to be SSX, SSS and then 1 X. So that is going to give us 3, and the stack is going to have 1 and 2. Next element is 2, so we need to have 1 more X. And the next element is 5, so we got to push 2 elements. So there has to be S and S, and then 5 has to be there, so there has to be a X. then again a S which is going to push S, then again a X which is going to give us S, and then 2XX which is going to give us 4 and 1. So this is how we would just try to find a string S and X based on the output which we need to get. And as you can see, for the number 154623, this is something which is invalid, because you can get a 1 and you can get a 5, 4, but you can't really achieve it. You can just work out through that sequence and try to achieve it, and you won't get the answer. Okay, the question number 15 is finding of spans. Given an array A, the span Si of Ai is the maximum number of consecutive elements Aj immediately preceding Ai, and such that Aj is less than equal to Aj plus 1. So I don't have a picture over here, but the book obviously has a picture, but we can still try to understand the question. So all it has to be basically a growing hill. If we are looking into Ai, say A10, all the elements before A10, say A9, is eligible to be considered in the span, because A9, if A9 is less than A10, and A8 is also eligible if A8 is less than A9. So it has to be a continuous decrementing order. The moment we encounter an element which is higher than the next index element, then the span breaks. And the span is the maximum number of consecutive such elements. So let's directly look into the code. So the method is called calSpan or calculate span. It takes nothing and returns void. So we have a for loop ranging from I to n, and what we do is we just check if Ai is less than As dot peak. So let's just run through this code from the very start. So initially the stack is going to be empty, so this condition is going to be false. So we would come to this point and we would just go and push an element to the stack. Now we go back to the for loop, and again we see if the stack is empty or not. So this is, we are working on the element A1. The previous element which was pushed onto the stack was A0. If the stack is not going to be empty in this case, and the current element Ai is less than As dot peak, so assume that this is not the case, and assume that Ai is greater than A0, A1 is greater than A0. So in that case, what we would do is we would not get into this if condition, because we just know that my elements are increasing. It's just getting added up into the string. So we would just push it to the stack once again. And then suppose the third element is also in a similar fashion. So this if condition again is going to be a false. So we would push the third element. So assume A0, A1, A2 was 2, 4, 5, and then 2, 4, 5. So these are the first three elements. And then the next element was suppose 1. So when we encounter a 1, we know that we can calculate the span for the first three elements, which is 2, 4, 5. So when we start processing the fourth element, which is 1, we would see that stack is not empty, and we would see that Ai, which is A3, and it has a value of 1, that is actually less than the topmost element of the stack, which is 5. So this means that we can calculate the spans for A3, A2 and A1. So that's the reason we start a while loop, and in this while loop we continue in this while loop until we encounter an empty condition. And what we do is we calculate the size of the stack by um, calling s.getTop, which is going to give me the top of the stack, and then do a +1 on that. And we also get the index is equal to s.pop, which is so what we are popping in the element is not the value of the element but the index of the element. And then we know that span of the index is the size of the stack. Whatever was the size of the stack is the span of this. It's the span of that particular element. Okay, so what is the nature of the stack? The nature of the stack is the stack has always numbers in ascending order. If the next element to be inserted is not greater than the top element of the stack, we calculate spans of all elements and then empty the stack. A stack is suitable because I know my span. I can calculate the span of the previous elements also. Alright, the next question is question number 16, which is largest rectangle under histogram. A histogram is a polygon composed of a sequence of rectangles aligned or having equal widths but may have different heights. For simplicity, assume that the rectangles are having equal width but may have different heights. Given an array with heights of rectangles, we need to find the largest rectangle possible. I don't have a picture over here, but a histogram, each of the array element indicates the height of that particular bar, and what we got to do is find out the largest rectangle in this histogram. So as we continue to find the solution of this problem, we would take an example. The example has numbers 2, 6, 7 and 1. So in this case, what 2, 6, 7, 1, we would, as we walk through the code, we would try to understand how do we get the answer. So the method is max rectangle. We have a for loop starting from 0 to n, I less than equal to n. So n in this case is 2, 6, 7, 1. So n is going to be 4 in this case. We have 4 elements and n is set to 1, n is set to 4. So when we are working out this loop for the first element, which is 2, at this point of time the stack is empty. So when you call peek on that, that is returning a 0 value, assuming that 0 is not a valid number. So if this is false, then what happens is this whole thing becomes false, and we basically will not enter into this while loop. And because this is the first and if one part is false, the entire expression is going to be false. So now this is the end of the while loop, and if I is less than n is equal to 4 and I is equal to 0, so which means that we are going to push 2 onto the stack. So the stack currently has 2, and at the end of the iteration 1, we have pushed the element 2 to the stack. Now we run this for loop for the second element, which is I equals to 1, and this has a 1 has a value of 6. So now we check this while loop, stack is not empty, so we check the second condition, if I equals to n, which is false, but we check this condition again, s.peak data is it greater than ai. So this is false again, because on the stack we have 2 and 2 is not greater than a1, which is 6. So we don't again enter the while loop. So we come to the end of the while loop, and if I less than n, so we go and push 6 again to the stack. The punchline here is that as long as the stack continues to remain in the ascending order, it is fine. So when we run this for loop for the third element, which is 7, again what would happen is that 7 is going to be pushed onto the stack, and we would not enter this while loop. So the stack now has 2, 6, 7, and now we run the for loop for the last element, which is 8, 3, and it has a value of 1. So the moment we see a 1, we see that the top of the element has a value of 7, and 7 is greater than 1. So at this point of time, we know that for the element 7, we have to calculate this the rectangle, because we have a number which is smaller than 7. So this rectangle which is formed by 7 cannot exceed on the right side, it can exceed only on the left side. So we pop 7 from the stack, and we see that after popping the element, if the stack has nothing, we set index equal to -1, which is not the case in our case. We get the index as the one which is for the element 6, which is 1. So index is 1, and we calculate the rectangle size as because the stack always has to be ascending order, so the element 7 cannot actually be present on the left side. It has to be guarded by that index. So the rectangle 7, the rectangle, we would calculate the rectangle for the element 7, and we would again compare if this is equal to the maximum rectangle size, which is not the case because this is the first rectangle which we computed. And so the first rectangle size is going to be 7. Now we continue in the while loop, and we check if 6 is greater than 2, which is the case, which means that 6 also which is greater than 1. So 6 also cannot, the rectangle formed by 6 also cannot cross the boundary of 1. So we pop 6, and we again check if there is an element in the stack. So yes, there is an element of 2 already in the stack. So we take index of 6, which is 1, and we take the index because on the right side there was an element higher than 6, so we need to consider that as well. So the rectangle formed by 6 is going to be there for 6 and 7, so 6 into 2, 12. The size of rectangle formed by 6 is going to be 12, so we again set that to 12, and this is the larger rectangle now. And then we iterate through, we come iterating for the third element, and we see that yes, there is an element which is 2, and 2 is greater than 1. So which means that the rectangle formed by 2 again cannot exceed the 1 boundary. So similar way we would get the index of 2, which is 0, and the rectangle formed by 2 can span the width of 2, 6, 7, but it cannot, it is guarded by 1. So 3 into 2, 6. Now this rectangle is smaller than the previous one, 6 into 2, so we discard this rectangle. And now we have basically, now when we again go back to the while condition, we would see that the stack is empty, so we would not just enter this while loop and push the element 1 onto the stack. And then when we come to the finishing loop, and so this is for I equals to 4, we come and check if I equals to n, we would enter the while loop and basically compute the size of the rectangle formed by 1, and index in this case is going to be -1, and the index of the current index is 4, so basically for this thing we would, for the rectangle formed by 1, we would calculate the area of 4 into 2, 6, 7 and 1, so 4 into 1, so 4, but still that is not a larger rectangle, so we would just continue, and then we have the answer, which is 12, which is the rectangle formed by 6. So that's how we calculate the largest rectangle. The important points to note here is that for every element we store the index as well, along with the value of the element. That is one thing. The second thing is the stack always has to be in the ascending order, but there could be missing elements in the stack. Question number 17. Evaluate the infix expression. Can we evaluate the infix expression with stack in one pass? This is just a simple question, and let's just directly go through the answer of this question. So we create an operator stack and create an operand stack and scan user input and do following. If the input is an operand, push it to the operand stack. If the input is an operator and has precedence greater than the top element of operator stack, then push it to the operator stack. Okay, let's start looking into the answer once again. So there are two stacks. One is the operator stack and the other is the operand stack. We scan through the user input. If the input is an operand, push it onto the operand stack directly. There is nothing to be done. If the input is an operator and has a precedence greater than the top element of the operator stack, then push it to the operator stack. So as long as the operator stack continues to be in ascending order of precedence, it is fine. You just keep pushing the operator to the operator stack. Else, pop an operator from the operator stack and pop two elements from the operand stack. Evaluate and then evaluate the expression and then push the result to the operand stack. And continue to pop the operators from the operand operator stack until the top element of the operator stack has lesser precedence than the red operator from the input string. So that's what we are going to do. And if there are no users input left, then pop operators from the operator stack and two operands from operand stack, evaluate and then push the results to the operand stack. So the solution basically revolves around binary operators, and let's take an example. So 2 plus 3 star 4, what would happen is we would push 2 and then we would get plus, and we would push plus into the operator stack. We would get 3 we would put the operand stack. When we get C star, so adding star to the operator stack does not change the characteristics of the stack, in the sense that it does maintain the property of being in the ascending order of operator precedence. So we push star and then we push 4 to the operand stack. Now we have reached the end of the input. So what happens is that we would pop star from the operator stack, pop 3 and 4, multiply them, put the result back to the operand stack. Then we would pop plus from the operator stack and then apply that to the two operands and then keep the result back to the operand stack. Now if this was 2 star 3 plus 4, we would put 2 onto the operand stack. When we get star, we would put star into the operator stack. When we read 3 we would put to the operand stack, and the moment we see a plus, we know that we can't add plus to the operator stack because that violates the nature of the stack which we just decided. So we would pop out star from the operator stack, evaluate and get two operands from the operand stack, 2 and 3, multiply them and keep the result 6 back to the operand stack, and then we would put plus to the operator stack. And now we have reached the end of the input, so we would pop up plus, get two operands, which is 6 plus 4, and then put the result 10 into the operand stack. So this is how the evaluation of infix expression is going to be done in one pass. This is similar to how we convert an infix expression to postfix expression. The only difference is that we need an extra stack to store the operands, and we just have to continue evaluating the operands when we get a operator of a lower precedence. So there are some more questions which I am not going to discuss, but let's just list down these questions. This basically talks about the problem where we had to calculate the min of the stack in O1. Now the additional question is that if there is a fourth operation, delete min, which finds and deletes the smallest element, then at least one of the operations must take O log n time. There was another question which is not there in this slide, but which is to check if a string is palindrome or not. So that again is a palindrome is, for example, A, B, C, D, and then there is going to be a separator X, and if the other part after X is D, C, B, A, this is a palindrome. So again, this is something which can be done using stack. Till you encounter the symbol X, you would push the element onto the stack, and the moment you encounter S, you would continue to read the input string and pop the element from the stack, and then compare if it is matching or not. If it matches and if the stack is emptied, it is a palindrome, otherwise it is not. There is another question which talks about implementing multiple stacks in array, and this is just a overkill and nobody would really want to do it, so I'm just skipping that. This is a little variant of the problem balancing symbol in C++ which we talked about, and the first part is the same as the previous one. The second part talks about printing out an error message which is going to reflect the probable cause, but I'm not going to discuss that as well. And the other is the infix to postfix conversion, and the last part is interesting here, which is write a program to convert a postfix expression to infix. So this is going to maybe require some thinking, and maybe let's just try it out. So stacks in general, in so many of the code bases which I have seen, stacks, at least in all the telecom application, this was not at all used in any of the places. There is not even a single place I find a use of stack. And even all these books, when we talk about application of stacks, they mainly talk about two things. One is when functions calls are happening, so that is a time where we make use of stack. The second thing is evaluation of expressions, conversion from infix to and postfix expression, and maybe when we have to do a balancing of symbol. So these are a couple of applications of stacks, but none of them are really eligible for a telecom kind of application. Thank you.